Welcome to some common indefinite integrals. So again, recall that the indefinite integral of lowercase f of x dx is equal to a capital F of x plus c, where the derivative of that capital F, I'm going to use the other notation here, our ddx notation. So the derivative of our capital F of x is equal to lowercase f of x. So the trick here, if we want to know an indefinite integral, is we need to know our derivative facts, and we need to know some function whose derivative is the thing inside of our integral. So let's just start off with the derivative. We're going to start off with the derivatives and kind of come up with the parallel indefinite integral. So the derivative of a constant c was equal to 0. So now we're going to go backwards. If we want to take the integral of 0 dx, then we should just get back out a constant. Right? So we're going from the answer essentially to the original function. If we're taking the derivative of x, and the derivative of x is just 1. And so we can go the other direction now. If we want to take the integral of 1 dx, that should take us back to that x, and then we have plus c. So these are all kind of giving us the corresponding indefinite integral. Power rule, the derivative of x to the n is n times x to the n minus 1. If we wish to take an indefinite integral, we're going to stick with x to the n instead of x to the n minus 1. That's the more common way of writing this rule. Notice when we took the derivative, our power dropped by 1. So when we take the antiderivative, our power should go up by 1. So we're going to have an x to the n plus 1. And then when we took the derivative, we took the original power and multiplied it out front. So the power before any derivative was taken. So that power would be our n plus 1. And since we're trying to undo, we should divide by n plus 1, right? So when we do the antiderivative, we're kind of doing the opposite of what happened in the derivative. If in the derivative we multiply by a number, in the antiderivative we should divide to undo that. And then we have our plus c. Right? So if we took the derivative on the right side here, x to the n plus 1, you would multiply by that power n plus 1, which will now cancel with the denominator. And then we just wind up with to the nth, which is precisely what we want. So this is kind of the power rule in reverse. So the problems in the last video, this would have come in handy, right? We have an immediate way to find an integral of any x to a power. Derivative of sine x was cosine x. And so the corresponding integral, we have the integral of cosine x dx should be, go backwards, we backtrack to sine of x, and then plus c. Next up, derivative of cosine of x was negative sine of x. And so we should have the derivative of sine of x dx. If it were negative sine, we would get positive cosine, but because it's positive sine here, we actually wind up with negative cosine x plus c. Derivative of tangent was secant squared x. And so that winds up going to, if we want to take the integral of secant squared of x dx, we backtrack and wind up back at tangent of x, and then plus c. If we have derivative of cosecant x, derivative of cosecant was negative. I'm going to actually do this down below. I don't have room there. This was negative cosecant x, cotangent x. And so if we write this as an integral, if we wish to take the integral of cosecant x times cotangent x dx, if this were negative, then we would get positive cosecant x. Since it's positive, we actually wind up getting negative cosecant x, and then plus c. The derivative of secant of x was secant x tan x. So when we take our integral, we take the integral of secant x tan x dx. We should get back out precisely what we originally started with, our secant of x, and then plus c. The derivative of cotangent of x is negative cosecant squared x. And so we're going to look at just cosecant squared, take the integral of cosecant squared dx. Again, if this were negative, we would get out cotangent x plus c. Since we have a positive cosecant squared inside the integral, we will actually get out a negative cotangent x plus c. That way, when we take the derivative, the two negatives will multiply to give us that positive cosecant squared. Derivative of e to the x was just e to the x. And so we get the integral of e to the x plus c. Sorry, the integral of e to the x dx is just e to the x plus c. E to the x is a very special function. It's its own derivative. It's its own antiderivative. Next up, we have derivative of a to the x was equal to the natural log of a times a to the x. So if we wish to take the integral of a to the x dx, essentially we're going to do the opposite of multiplying by natural log. We should divide by natural log. So we'd have a to the x divided by the natural log of a, and then plus c. Then we had the derivative of natural log of x was 1 over x. And we get that the integral of 1 over x dx, we have a natural log of x, but it actually turns out we can do this for both positive and negative x. It winds up being the natural log of absolute value of x, and then plus c. And next up, the derivative of sine inverse of x. We had 1 over the square root of 1 minus x squared. So if we wish to take the integral of 1 over the square root of 1 minus x squared dx, this is just inverse sine of x plus c. Similarly, the derivative of inverse cosine was negative 1 over the square root 1 minus x squared. So it turns out that this is essentially equivalent to the previous one. We actually get that the integral of 1 over the square root 1 minus x squared dx could also be written as negative inverse cosine x plus c. So these are equivalent. Not cosine inverse and sine inverse, but once we add for that shift, we get an equivalence. All right, next up, we have the derivative of inverse tangent. We are looking at 1 over 1 plus x squared. So if we wish to take the integral of 1 over 1 plus x squared dx, this is just tan inverse x plus c. Next up, we have the derivative of cosecant inverse x. This was negative 1 over the absolute value of x times the square root of x squared minus 1. And so we have the integral of 1 over the absolute value of x times the square root of x squared minus 1 dx is equal to, I didn't put the negative inside here, so we're going to have to do the negative in the answer. We have negative cosecant inverse x plus c. We wind up here with an equivalent statement. We have the derivative of inverse secant was 1 over the absolute value of x times the square root of x squared minus 1. And as an integral, this will become the integral of 1 over absolute value of x times the square root of x squared minus 1 times dx is equal to, this was positive in the derivative format, so this is what we want. We just get inverse secant x plus c. And then cotan inverse, the derivative of cotan inverse was negative 1 over 1 plus x squared. And so this would be integral of 1 over 1 plus x squared dx. I didn't have the negative here, so I'll have to do the negative in the antiderivative. We get negative cotan inverse x plus c. So again, because the derivatives just differ by positive or negative, we wind up getting multiple inverse trig functions. When we look at the integral equivalent, we're basically working with the same integral. But these are a series of basically all of the derivatives that we have learned using specific functions. And now looking at their the corresponding integral. Just a side note, the one strange one was natural log and 1 over x. So just a side note. So looking at the integral of 1 over x dx being natural log of absolute value of x, plus c, right? If f of x, sorry, this is our capital F. So capital F of x is that natural log of absolute value of x. That means that we are looking at natural log of negative x for x less than 0, and natural log of x for x greater than 0. We can't take natural log of 0 itself, right? But we also can't do 1 over 0. So natural log, we can separate. So this is natural log of negative sorry. If we take the derivative of this, natural log of negative x is just the mirror image of natural log of x, right? Because absolute value is. So if we think of it in terms of a mirror image, all we're doing is sort of flipping the derivative to the other side, right? And so when we take the derivative, all we're doing is we're flipping its direction and changing it from increasing to decreasing. And so if this goes to 1 over x, this also winds up being actually just 1 over x, because we do want the negative involved over there. So we do wind up getting sort of what we were looking for when we started. Again, we know that natural log of x, which is our right side, will go to 1 over x. That is the derivative of natural log. And then since we just have mirror image on the left side, that mirror image just winds up having the negative slope instead of the positive.